All right, so the next problem is about voltage. And there's some misconceptions that I'm hoping I can clear up right here at the beginning so that it doesn't continue to bother people later on. And that's how we measure voltage and how we denote voltage on circuits. So the way we label voltage sources is if I have a voltage source and I have a plus and a minus, what that means, and I have a 5 here. So I've got my voltage source, I've got a plus and a minus, and I have it labeled as 5 volts. That means the positive side is 5 more than the negative side. So if I make this ground I'd say is 0, then on the other side of this, on the positive side, it's going to be 5 volts. Or if I have, let's say I have this, and I have calculated that here it's some voltage, maybe it's 10, I've calculated that, and here it's 6, and I have this labeled as negative 2 volts. That's the labeling. That means that the positive side is negative 2 more than the negative side, or the positive side is 2 less than the negative side. So if this is labeled as negative 2 volts, that means the negative side would be at 4 volts. So when this has a negative voltage, then the positive side is lower than the negative side by that amount. So the label on the voltage source is very important. It tells you what the difference is between the positive side and the negative side. But it can be labeled however you want to label it. That's... It just is, it's how it's given. So it can be given as a positive voltage source and be given as a negative voltage source. But that's how it works. So what is voltage?
Energy per unit charge, or the potential difference across 2 points.
Yeah. So what voltage is potential energy per unit charge, which you will use a lot in physics and you don't use often in circuits. In circuits, you basically want to think of voltage as kind of the pushing force. It's what makes the current go. And so current is going to travel from high voltage to low voltage. So if I have something that is at 10 volts here, right here, and it's at 3 volts here, the direction of the current is going to be in that direction, or the direction of positive current is going to be in that direction. Now, that is not what happens in a voltage source. A voltage source is designed to take charges from lower potential and move them up to higher potential. And so that's why if I have a voltage source right here that's 10 volts, that the potential is going to be 10 volts higher on the positive side than it is on the lower side. Power is energy over time, or in calculus, it's dE dt. So it's the rate of energy. And power and voltage and current are related through power equals voltage times current. And this is the definition of power that I always remember. P equals IV. And then with Ohm's law, you can get that into other forms as well. And the way we look at this, and this tends to cause a lot of confusion, is you have to remember that the way we label things doesn't necessarily tell you what is actually necessarily going on. So if you look at this element, this top element right here, it's labeled, there we go, it's labeled as having the positive terminal on the left and the negative terminal on the right. And the current is drawn as going in. So that's what we're kind of defining as positive current. It doesn't mean I is positive. It's saying that this is the direction we're saying current is going. That's the direction I is going. And so the power here is I times V because it's coming into the positive side. If we look at number 2, the current I as drawn is going into the negative side, and so we say P is minus VI. In the third one, we have the current on the left, but that's the way it's drawn. And so the current as drawn is going into the negative terminal, so that's negative VI. And the current as drawn here, I, is going into the positive terminal, and so that one would be positive VI. Now that's doing the calculations. Whether VI ends up being positive or negative itself is going to tell you whether or not the power is being supplied or absorbed. So a negative power means that you're supplying power, and a positive power means that you're absorbing power. That is the answer after you've done the multiplication. So that answered part E. And now let's go to the problem. It says, given that the current due to electron flow is due to electron flow state, calculate the power at the terminal. The numerical values for V and I are 80 volts and negative 4 amps, and we're supposed to use figure C. So V is given as 80 volts. I is given as negative 4. And this is the minus side and the plus side. So what this means is the power is equal to minus IV because I'm coming into the negative side. When I write this, I don't care if I is positive or negative. I don't care if V is positive or negative. The only thing I care about is that I is entering into the terminal labeled negative. So I've got this, I've got minus, plus, and I've got I. And I've got some voltage. And so I say power equals minus IV. Now I go and look at my values of I and my values of V, and I plug in. I is minus 4 amps, and V was 8 volts. And so negative 4 times 8 is going to give me 32 watts. Okay, So calculate the power and state whether power is being absorbed or delivered by the element in the box. So, is power being absorbed or delivered?
Absorb.
Power is being absorbed because it's positive. Okay. Given that the current is due to electron flow, state whether the electrons are entering or leaving terminal 2. So this is 1, and this is 2. Now I do have to pay attention to the sign. So I is negative 4 amps. So what that means is that conventional current, positive charges are moving this direction. So a positive current means positive charges are moving in the direction of the arrow. A negative current means positive charges are moving opposite the direction of the arrow. So what direction are electrons moving?
Opposite direction.
Yeah, opposite direction. So if positive charges are moving this way, then actually what's happening is electrons are moving to the right. So are electrons moving, entering or leaving terminal 2? They're leaving terminal 2. Do electrons gain or lose energy as they pass through the element in the box? Okay, well this, I don't, well let's think about it. So, we have our voltage was 80. That means this side is a plus 80 volts and this side is 0. So we have a higher potential on this side. So if I were a positive charge, I would be losing energy going from 80 to 0. So going, wait, what does it say? Passing through the element in the box. Okay, so the electrons are actually moving this direction. This is not going to be on your test. This is just kind of concept stuff. So electrons are moving this direction, going from a lower potential to a higher potential. Are they gaining energy or losing energy?
Gain.
Gaining.
Electrons?
Yeah, they're going to a higher potential.
Okay, so potential energy is so positive charges gain energy as they go from low potential to high potential. So positive charges gain energy this way. Negative charges are going to lose potential as they're going from lower to higher. So the potential energy here, so we said it's the potential energy per unit charge. So you would have, but you have to pay attention to the sign as well. Yeah, this is something I'll make a video about and explain later, but just for right now, just accept that positive charges gain energy going from lower to higher potential, and negative charges lose energy going from lower to higher potential. Think of positive charges the same as gravity. So if I'm a positive charge and I'm going from low potential to higher potential, going uphill, I am gaining potential energy when I do that. But negative charges work the opposite. You're just not used to it because we don't have negative gravity, but we do have negative electricity. Okay. And I think that was it for this one. Oh, yeah, okay. So now let's take a look at this car battery. Okay, so I've got that the current is flowing in that direction, and I don't think I told you, but it is a positive current. And so which car has the dead battery if I'm charging it this way? Can you tell from this picture?
It would be.
It would be the red car.
Yeah, and why do you say that?
Okay, so kind of going back to the last question that you had, so dealing with batteries, if you have a fully charged battery, it would have more electrons on the negative side, and so they can have a higher potential because when the batteries flow, actual current flow goes from negative to positive, which would, if it's all the electrons are on the positive side, it would essentially be a dead battery. So if the blue car is sending electrons to the red car, that means the red car has a lower potential and its gain potential of electrons on that negative side terminal.
I honestly can't tell you if what you said was right or not, because it probably was. I was thinking of it more simplistically. I was thinking of it just in terms of power. And if I'm looking at the red car, I think you were probably right, but if I'm looking at the red car, I see that my positive current is entering into the positive terminal of the battery, and so that gives me a positive power. So P equals IV, and when I have a positive power, that means that power is being absorbed. And so since it's being absorbed, that's going to be the car that has the dead battery because it is gaining energy. And that probably goes along exactly with what you were saying, but I wasn't quite able to follow, but I think it was probably good. Did that match with what you were saying?
Yeah.
Okay. And then I think I needed to give you the actual current in order to be able to solve this problem. So let's see, this is circuits 2. And yeah, okay, so if the current is 25 amps, so if the current is 25 amps, so I is 25 amps. I apparently can't write on this. So the current is 25 amps. Then my power is I times V. So that's 12 volts times 25 amps. Or my power is 300 watts. And 300 watts, that's the same as 300 joules per second. And if that connection is maintained for 1 minute, then that's for 60 seconds. So that would be 18,000 joules or 18 kilojoules. All right, any questions on that before we go on to the next one?
The current you just said, the 25, is that just something that you can choose?
I forgot to put it in the problem.
Okay,
Yeah,
right.
yeah, I forgot to type it in.
So it will change.
Yeah, it would change. Other questions?
Whenever we're dealing with time and power, it's always going to be in joules per second or kilowatts per hour.
It is usually going to be in joules per second. If they could be in it could be in hours, but watts is always in seconds, and so kilowatt hours is kind of a confusing unit. Let's talk about kilowatt hours. So if I have a watt is a joule per second, but you will often deal with kilowatt hours. So a kilowatt hour is 1,000 joules per second times 1 hour, or 1,000 joules per second times 3,600 seconds, or 36,000,000 joules, or 3,600 kilojoules. So a kilowatt hour is actually a unit of energy. But whenever you're dealing with power, the unit that you get from multiplying current times volts is a watt, and that is a joule per second. So the main answer to your question is yes, it's almost always going to be seconds. They could give it to you in different units in the problem, but then you'd have to convert. Other questions?